Hello, everybody. So glad to be with you again. I'm Professor Steve Rehse from the University of Windsor in Windsor, Ontario, Canada. And I'm very pleased to be joining all of you talking about our GALE Forces seminar this month, where we're having a bunch of really cool STEM talks related to weather conditions and things that you might know about weather. So today I want to talk about a topic, just some research that I've been involved with just a little bit in all my years as a physicist, where we can use lasers to measure the conditions of the upper atmosphere, and that'll help us with our predictions of weather. So let's jump into that and see what that's all going to be about. We have to start off today with our land acknowledgement statement, of course. The University of Windsor, where I work, sits on the traditional territory of the Three Fires Confederacy of the First Nations. This includes the Ojibwa, the Ottawa, and the Potawatomi. We respect the longstanding relationship with First Nations people in this place, in the 100-mile Windsor-Essex Peninsula, and then the Straits, Les Détroits of Detroit. So let's talk about weather on Earth. What do we mean by weather? Well, when you use that word weather, and you all know it, what's the weather like outside? So weather typically means our day-to-day conditions of the atmosphere. Temperature, is it hot or cold? Precipitation, is it raining? Is it snowing? Is it foggy? Humidity, is it dry? Is it moist? Air pressure. Everything that we call weather is caused by heating and cooling of the atmosphere. That's caused by the sun and the effects of that heating and cooling on the air, the land masses, the oceans, and the ice sheets on the Earth. And the rotation of the planet plays some role as well in driving all these patterns. So that's what we mean by weather. Climate is actually something else, right? Climate's typically the term for the averaging of atmospheric conditions over longer periods of time. This could be decades, centuries, millennia, etc. So we're going to be talking about weather today. So like I said, weather is what's going on in Earth's atmosphere. What is Earth's atmosphere? Well, there's this gas that surrounds our planet Earth. It looks like this beautiful blue layer of gas in which we all live. And we kind of divide it up into some arbitrary zones as you increase in altitude away from the surface of the Earth. Almost everything that you know and experience as weather takes place in what we call the troposphere. All right, so here is Mount Everest to scale. So all the weather is basically up to about the height of Mount Everest, 10 kilometers up. But the atmosphere doesn't stop there. There's a lot going on in those upper layers that we don't experience down here on the surface of the Earth, but are critically important for determining what does happen in the troposphere that we experience as weather. Above that, there's this region that we call the stratosphere, and above that, the mesosphere, and finally, the thermosphere, up near where the atmosphere disappears and you're actually going into outer space then. You can see there's no sharp line here where the atmosphere ends and space begins. It just kind of trickles off. So atmospheric measurements in all those different layers. What would we like to know as scientists? What is it that we have to measure? Well, we'd like to know atmospheric composition. So we mostly know what air is, of course, molecular nitrogen and oxygen that we breathe. There's other minor constituents in the atmosphere: water vapor, carbon dioxide, methane, CFCs, and ozone. These are all things that they're up there, and we want to know where they are and what concentrations, because this has a lot of impact on our weather. We'd like to know about the clouds, of course. Clouds are just moist air in the lower atmosphere. Different types of clouds form at different altitudes, and they're an indicator of the atmospheric stability. What's going on? Motion. Is it stable? Is it restless? Is it turbulent? And then we'd like to know about the dynamics of the atmosphere, the temperature, right? What is the average temperature in each of these layers? And the temperature changes very dramatically from the surface of the Earth as you go up into space. Of course, we want to know about the wind. Wind patterns develop due to these temperature differences between the different layers. And also there's this rotation, and then there's pressure differences all over the surface of the Earth. And these are going to cause regions of pressure to move from one place to another. And we experience that in the troposphere as these winds. And then there's this thing called waves. And they're sometimes called planetary waves. And these are actually oscillations of conditions that can go up and down, rolling through the atmosphere like a convection, right? So this is just like the bubbles in a pot of boiling water are coming up from the bottom. They're bringing that hot water and stirring it all up. We get these waves of motion through the atmosphere. And that it's a really important part of the dynamic nature of our atmosphere. We'd like to know more about that. If we could know all those things, let's just say and pretend we could know them. We can't, but what if we could? What would we like to do with those things as scientists? Well, we would like to use it for way better weather forecasting. You ever wonder why the weathermen, they can kind of know what's going to happen in a day. If you're lucky, they're going to be able to predict what's happening on the weekend, but they don't know what it's going to be like in 2 weeks, 3 weeks, 4 weeks. Why? Well, we would like to develop predictive models. We have calculations. We try to model the physics of what's going on in the atmosphere. And this would allow us to predict in the short term, to days and months, and even long term, months, years, decades, out into what's actually called climate, if we could actually understand what's happening in the atmosphere well enough. So what we'd like to do is improve our understanding of all those physical processes I was talking about before, and then we can incorporate those data and our better understanding of the physical processes into these models and basically be able to predict the weather much more accurately, which everybody would really enjoy. So how do we get these measurements? What it really needs is a lot more measurements. We really need to know what's going on in the atmosphere. Well, one of the ways we do that is with balloons. So here's a picture of a guy releasing a weather balloon. Every 12 hours, hundreds of people all over the world release these huge white balloons that you're seeing here up into the sky, and the balloons float upwards, each tethered to a box of instruments at the bottom, and that collects data as it rises up through the atmosphere. There's no pilots, there's no engines. It just kind of goes up and floats, and then it moves with the wind. In 2 hours, the weather balloon can rise above the clouds, right? So let's look down on our diagram here. So here's us on the surface of the Earth. Here's the clouds. Here's where the weather balloons are getting up to, up in the stratosphere. So they're going above the clouds, higher than the path of jet planes, right? Here's all the jet planes. I don't know how many of you have ever been on a jet plane. The weather balloons are going higher than that. They're going up to altitudes of like 35 kilometers, which is 22 miles or even higher. They have to endure extreme temperatures. It's called as minus 90 degrees centigrade. And depending on the winds, the balloons can drift easily more than 200 kilometers from the place where it was released. All right. They can rise quite quickly because they're big, about 4 meters per second. And they take about 2 measurements of the atmosphere every second. So it's possible for a balloon to collect data about every 2 meters as it goes up through the sky. And these instruments measure temperature, air pressure, humidity, wind speed, and wind direction. All those instruments would be hanging underneath the balloon like this. And then a radio signal is going to beam those measurements back down to scientists on the ground. And we just do this day after day after day after day all the time to keep always accumulating data, because if you take some measurements last week, well, that's not going to be helpful predicting what's going to happen in the next week. We need the current measurements all the time. So we saw that the weather balloons only go up into the stratosphere. What if you wanted to go actually higher than that? Well, we use things called rockets or weather rockets. So a weather rocket, which I'm showing in this really cool picture here, is a specific type of what we call a sounding rocket. All right, and it's going to go up and take these meteorological measurements in the upper atmosphere. So here you can see it kind of going up into the mesosphere at altitudes of roughly, 75 kilometers, about 40 to 50 miles. You can see up here this sounding rocket way up above where the weather balloons can actually reach. So in a typical weather rocket, after launch, the rocket, which is here, and the payload section, which is up here, will separate at a set height. The rocket motor will fall back down to Earth. We can grab it and reuse it. The instrument payload will continue its ascent. It's much lighter now, so it can go up a little higher until it reaches its apogee. And apogee is just a word that physicists use to mean the highest point of an arc, or the furthest distance away in an orbit. And then it'll start taking measurements with the assistance of a parachute as it falls back down to Earth, which can be done very, very slowly. Again, not controlled, not piloted, just kind of falling under its own, but slow enough to get measurements. And so two of the biggest advantages of using a weather rocket is you can reach much greater altitudes than the weather balloon, and you can do it in a fraction of a time. You don't have to wait for it to drift up to the upper atmosphere. The rocket just takes it right there, right away. I'll bet you here's something that all of you sitting at home have seen, the famous radar map. You've all turned on the weather and see, I want to see what it's going to be like tomorrow. You turn it on, you're going to see some picture like this. Here's a radar image of a hurricane coming into southern Florida. What is radar? Radar is an acronym of sorts for a phrase called radio detection and ranging. RADAR, radar. In radar is just radio waves which are transmitted into the atmosphere. So radio waves are just a type of wave on what we call the electromagnetic spectrum. And there's all kinds of things on the electromagnetic spectrum. from long wavelength radio waves. It's the way that Wi-Fi works in your house. It's the way your cell phone is communicating with the cell phone towers. Electromagnetic radiation is the light that we all see by, the light coming from the sun. It's the ultraviolet rays that come out of a tanning bed to make you tan. It is the X-rays that doctors and physicians use to image inside your body. It's all of this form of electromagnetic radiation, and they have very different properties depending on what the wavelength or length of those waves is. So radio waves are actually pretty long, and this is great because they propagate a long, long way through the atmosphere. So we have central towers, which looks like this right here. So this would be a radar radio wave antenna. It's shooting a large amount of radio waves out into the atmosphere. Those radio waves scatter off all the stuff in the atmosphere, and some of that radio wave is scattered back to the radar's receiver to form an image that looks like this. Well, it turns out you can do kind of the same thing with light. So remember, radio waves were down here, but light is just another form of electromagnetic radiation. So you can shoot light electromagnetic radiation out into the atmosphere. And when you do that, that's called LIDAR. So a LIDAR can kind of be thought of as a laser radar. LIDAR is an acronym which stands for light detection and ranging, just like radar was. So in LIDAR, you shoot this electromagnetic radiation, which is at a much higher frequency or shorter wavelength than those radio waves. And that's going to give us some advantages. So LIDARs can operate in a couple different regions of the electromagnetic spectrum down here, which could be visible to your eye, or it could be longer or shorter than what's visible to the eye, called ultraviolet and infrared. And LIDAR can actually probe different types of physical processes. Remember, I said we wanted to know about those. So different types of processes can cause again, the reflected light. We're going to shoot a high intensity laser out into the atmosphere, and we're going to wait for some stuff to bounce back to us. And from that stuff that gets bounced back, we can measure atmospheric composition, temperature, and wind, and some other things as well. So here's some super cool pictures of what it looks like. A LIDAR's transmitter is a laser. So here, this is obviously a green laser in both cases being shot up into the sky. And its receiver is an optical telescope. So if these things look like astronomical observatories, they probably are. And I'm going to talk about how these lasers are also used in astronomy by shooting them up into the sky a little bit. But you need a big telescope to collect all that backscattered light. So you need a very powerful laser, and you need a really big telescope to collect as much light that comes back as possible. So some of you might be thinking, geez, can that laser actually like reach up to 70 kilometers, 80 kilometers, 90 kilometers? I wonder how high a laser can shoot up into the sky. Would you believe it? A laser can shoot all the way up to the moon, and it does. You bet it can. All right. So lasers don't just stop on the upper edge of the atmosphere. They keep going. In theory, they keep going forever. And if we're careful and we shoot these lasers at the moon, we can get bounces of that laser off the moon. And to help this, they're actually bouncing that laser off of mirrors that we call retroreflectors, which are set up on the moon. These are actually on the moon. So these are pictures from the Apollo 14 astronauts actually placing these retroreflectors. You can see the astronaut here and the lunar module next to this thing that they've permanently placed on the moon. So it looks like it's about roughly 1 foot by 1 foot square. And the laser radiation from the Earth is going up to the moon. These things are still there today, bouncing off that retroreflecting mirror, coming back to the Earth. And we can make extremely precise measurements, very accurate measurements of the absolute distance between the Earth and the moon all the time using these retroreflectors that are up on the moon. Very, very cool. And we're very much indebted to the astronauts for taking that up there with them. So let's give you some examples of some things that I've been a little bit related with in my life. I'll start with the Purple Crow LIDAR. All right, so Purple Crow LIDAR is at Western University. When I was there, it was called the University of Western Ontario in Ontario, Canada. It's now called Western University. And the PCL, Purple Crow LIDAR, is Western's atmospheric LIDAR system. So the Purple Crow LIDAR measures temperature with those waves that I was talking about, not waves in the ocean, waves of the atmosphere, and water vapor. And you can measure the temperature in at least 2 different ways. So one is a sodium resonance, which I'll talk about a little bit, or fluorescent scattering. The temperature can be measured using Rayleigh scattering. So how much light actually scatters off of the molecules will depend based on the temperature of the upper atmosphere. So here's a picture of the Purple Crow LIDAR being shot up into the atmosphere. And it looks like it's, occurring right as sun is setting. One of the things I wanted to talk about with Purple Crow LiDAR system is they did a really neat thing. Remember I said you need a big telescope, a big mirror to collect all that light that bounces back. It's not all that light. There's very little light that bounces back. So if you want to collect it, you need a really big light bucket to collect all that light that comes to you. These mirrors are super expensive. They're heavy. They can get damaged easy. They're not easy to make. So how do you do that? Well, astronomers and physicists have come up with something really cool. So this is a picture of the mirror that's collecting the light bouncing back from the atmosphere of the Purple Crow LiDAR, and it's called a liquid mirror telescope. Liquid mirror telescopes, or LMTs, they use a liquid metal, a metal that's liquid at room temperature. And two common examples of metals, real metals, that are liquid at room temperature are mercury and gallium. And this is actually a mercury liquid mirror telescope for the Purple Crow LiDAR. So this thing that looks like a bright, shiny steel mirror is not. This is a pool of liquid mercury that these physicists are standing around right here. So this by itself would make a good mirror, but it's flat. To be acting as a telescope, it needs to be curved. So what you do is this entire container will spin, not real fast, 6 revolutions per minute. So that's not super fast, but as it spins, the surface of the liquid metal actually flows out as things that are spinning do, and it'll form a parabolic surface, which is then ideal for a reflecting telescope to collect these LiDAR measurements. So with this reflecting liquid mirror telescope, the Purple Crow LiDAR scientists can have a mirror which is larger in diameter. This is about 2.65 meters across, larger in diameter than the Hubble Space Telescope, which is cool because with the liquid, it's just much easier to get that perfect shape. Those big mirrors are really expensive and really hard to make perfectly, which they have to be. Well, for a while, I also worked at Colorado State University. So Colorado State University, turns out, also had a LiDAR system. This was a sodium vapor LiDAR. So the interesting thing that I did not know about this at all until I went to Colorado State was that there is a natural global layer about 3 miles thick of sodium atoms up at around 80 to 105 kilometers. I'm showing it here on this map. It's just floating around it there. So many of you may have heard of sodium. So if you know anything about sodium, you know that table salt, a lot of people know that. Table salt is NaCl, sodium chloride. That's the sodium I'm talking about. That's exactly it. But these sodium atoms are not bound to a chlorine atom to make a salt molecule. It's just sodium all by itself. It comes from the ablation of meteors. Meteors come in from outer space all the time, much more prevalent in the early ages of the Earth, but still all the time. And as those meteors ablate and all the material gets blasted off of it, these sodium atoms just go up into the atmosphere and they just hang out at this region of about 3 mile thick layer between 80 and 105 kilometers. There's just this layer of sodium floating around in the air up there. You wouldn't be able to see it. It's very dilute, but there it is. So these atoms can emit a weak glow when they're hit by a laser. So another way you might know something about sodium, although it's not as common anymore because we're replacing all of our streetlights with LED, right? I don't know what you have outside your house. Are they LED streetlights? But the older ones were sodium vapor lights. So if any of you watching this live anywhere where the street lamps have this yellow glow, that's sodium. That's a sodium vapor street lamp. And that yellow color is the color that sodium gives off when it gets excited. So that's the color that we're going to want to be looking at, and we're going to shoot a laser up there to cause those atoms, which are not very many, but when you hit them with the laser, they're very bright and they give us this yellow light, and we can see all the way up to about 100 kilometers from those glowing sodium atoms. Super cool. So with that emission from the sodium atoms that get excited when we hit them with the laser at 100 kilometers, and we can measure temperatures and the horizontal wind velocities up there in the mesopause, right? Way up there. And we can make those measurements day or night because it doesn't really matter what's going on around those sodium atoms. It's just an interaction between the laser radar, the LIDAR, and the sodium atoms. And this will give you ideas about the atmospheric dynamics, gravity waves, tides, seasonal variation, solar cycle effects, etc. Right? So this is kind of a image of what that sodium layer might look like up there, and then even a meteor coming through to show you that, yep, meteors are still bombarding Earth all the time, so there's always a fresh source of some amount of sodium coming into the upper atmosphere. Here's a cool thing for you astronomy fans out there, the sodium vapor LiDAR, the same type of laser system. Here's a beautiful picture. Now, this is an astronomy application. So here's an observatory. they're looking up into these beautiful stars up here. They use this exact same type of laser system to create what are called guide stars for astronomical observatories. So a lot of these observatories now, so here this observatory, this telescope is looking up into space, but nearby it'll have this laser which shoots a beam up into the sky. And what it does is it creates a perfect little star, a perfect little point of laser light that's very well known, and it's known exactly where it is, and it's very, very sharp. And because this perfect little guide star is up there, we then have different ways of correcting our mirror, sometimes with calculations, and sometimes actually these things called deformable mirrors, which they can correct for the blurring due to the atmosphere. So for example, here's a great picture of one of the planets, and you guys know which planet this is. So we don't even have to talk about that because we've talked about those planets before, but this is a ground-based image of that planet taken through our atmosphere. It's very blurry, right? You're having a hard time seeing what's going on in there. That's because the light from the planet is perfect, but it gets all distorted and scrambled by the atmosphere and all the temperature fluctuations in the atmosphere. And that happens very quickly. You can't correct for that. But with that guide star in place, you can engage what we call adaptive optics. So we're adapting to those fluctuations in real time, and we sharpen up that image, and we get this beautiful Earth-based picture of our solar system, right? So all due to shooting a laser up into the atmosphere. Super, super cool. That's just a couple applications. Shooting lasers up into the sky has a lot of different applications. And this was just one of them, right? So I'm just talking about the weather measurements, although I hinted about another one, which was acting as a guide star to improve our astronomical observations. And I also talked about being able to measure the distance between the Earth and the moon really accurately. So there's way more applications than that. So this ability to control laser radiation, shoot it up into the sky, and then collect the signal that comes back from it has a lot of really useful applications. That's all I have for you today. I hope you really appreciated this idea of, again, how does a physicist think about the weather and the atmosphere, and how is it that we can get measurements from way, way up there? And these measurements are what can help us improve our models of the atmosphere, which will hopefully allow us to predict the weather a lot better. Well, that's it. Thanks, everybody. I look forward to chatting with you again in the future. I'll hang around for a little while after this talk, and maybe we can chat about some of these things. If you have any questions, you post them down there in the chat. If not, I look forward to talking with you again next time. Thanks a lot.